All right, good morning, chemists. We'll get started now. Plan is to finish chapter 1 material and then get started on chapter 2. All right, so we left off on Tuesday putting all of our measurement skills together and some of our significant figure calculations for multiplication versus division together in this slide, where we try to determine if this ring from a flea market is in fact pure gold or not, given its mass and volume via water displacement. So we took the difference between the two water measurements. This is subtraction. To get the volume of the ring, we see that these two volume measurements have technically 3 sig figs, but because it's subtraction, we are not counting sig figs. Our answer needs to go out to the same number of decimal places. So we see that the volume of the ring only has 2 sig figs. And that's important for the next step, division, for our density calculation. 4 sig figs over 2 sig figs gives us 2 sig figs in our density. So 19 grams per centimeter cubed. And so if we compare this to the table values, we can probably deduce that this is pure gold, because our calculation here is closest to gold. There's not really anything closer to that, right? And so lots of measurements here. Some of them volume, some of them mass, and some are calculated. So I didn't really know where to put this slide, but you'll be taking measurements in lab. Some of them are extensive in nature, some of them are intensive in nature. And so the difference between these two types of measurements are extensive measurements will vary from sample to sample. That, like, for example, the mass of something changes depending how big your sample is. The volume of something that you measure using a volumetric like a beaker will change depending on how much sample you have. So extensive properties, I like to think, will change depending on how much your sample extends or how big it is, versus intensive properties. These are properties that don't change sample to sample, so things like color, concentration, as long as you're working with the same like stock solution, density, and that's related to how we identified our gold sample up here, comparing the density of this sample to the density of gold in all samples. And so intensive properties are independent of size of your actual sample. Gold will always have the same density, whether you have a small flake or a huge bar of it. And so what often we can do is identify samples using intensive properties. So if we look back at this question and look at all of the measurements, are they intensive or extensive in nature? So the mass of this sample, intensive or extensive, that you measured? Extensive, yeah, because it'll change. If we're talking about a ring or a bracelet, that mass will change. What about these volumes? Also extensive, because it's water. And we see, look, the volume changes. And then, so there we go. And then density. Intensive. Yeah, so note here that, if we calculated the density of the ring versus like the density of a gold bar, like a gold bar is much bigger. So how will the mass differ for a gold bar if we did the exact same experiment? Mass will be bigger, volume will be bigger, but the density, the ratio of mass and volume will stay the same, right? And that's specific to that sample via its identity. All right, so that's measurements. So now we'll get to my favorite part of the chapter, which is dimensional analysis and canceling units. It's one of the most powerful skills a scientist can have, to just be very clever with skills. So no longer do you have to memorize, do I need to divide or multiply to get to the answer that you want? So I urge you, whatever you learned in high school, if that's what you learned in high school, like memorizing, multiplying or dividing, just let go of that and just let me teach you the right way to do it, and being clever with units and canceling things out. If you get really good at it, you don't have to memorize any equations ever if you get really good at units. So the idea of dimensional analysis is to cancel units throughout a calculation. And so we'll be multiplying by a bunch of fractions that have different units on the top and the bottom. And so one of the big skills is being able to collect equalities, so something equals something else, and putting them on the respective top or bottom to cancel out that unit. So all of these equalities give us conversion factors that we multiply throughout our calculation. So let's look at some examples and how we can't use it. So here's a definition that we would give you in a problem. We could say something like 1 inch equals 2.54 centimeters. And so the whole point of the conversion factor given this equality is we want to set one side of the equal sign to the other side of the equal sign, right? And depending on what our calculation is, sometimes 1 inch will be on the bottom and centimeters will be on the bottom, inches will be on the top, centimeters will be on the bottom, or depending on the calculation, inches will be on the bottom and centimeters are on the top. So do note that like the 2.54 always goes with the centimeters, all right? So it's one side of the equal sign over the other side of the equal sign, whichever way you want to do it, all right? So there's one equality. Here's another example. Here's a definition. 1 meter equals 100 centimeters. That's a prefix you need to memorize, but depending on the calculation, you may want to put centimeters on the bottom and 1 meter up top, depending on what you're multiplying, or you can put 100 centimeters up top, 1 meter on the bottom. It doesn't matter. Well, it matters in the context of your question. We're allowed to use either one, depending on what we want to do. All right. So all of these fractions are what I call conversion factors, changing one unit to another. So for example, if we used this conversion factor, we would be changing the unit of centimeters to inch, right? So how do you know which conversion factor to use? Do we use this one or this one in a calculation? It's all about canceling units. Look at the unit that we're given, that's in our numerator. Put whatever you want to cancel on the bottom of your fraction, so your denominator, so they cancel out, and you put whatever you want up top. And that's how you get your new desired unit. So let's go back to this definition. 1 inch is 2.54 centimeters. So remember how we can set up the fractions if we want. And recall this is an exact definition. So that we'll have to apply that for sig figs here. So let's convert centimeters to inch. So our strategy here is start with the piece of information given and then take the equality and think, okay, what side of the equality do I want to put on the bottom? What unit do I want to put on the bottom? The 1 inch or the 2.5 centimeters? To the 2.54 centimeters on the bottom. Yes, because then that cancels, okay? And then put 1 inch on top. And then we get some answer. I don't know. 49.2 inches, all right? So I did not memorize, I need to divide by 2.5 to convert centimeters to inches. That's just dumb. Don't do that. Don't do that. Just look at the units and cancel them out appropriately, right? Because we're going to be making a lot of different conversions. Do not fill your brain with those memorizations when things can just be figured out by being clever with units. Let's inspect sig figs here, because people have asked me about sig figs and dimensional analysis. How many sig figs are in the measurement that's given to us? 3. How many sig figs are in this definition? Infinite, yeah, because what's the detail here? They're exact. So how many sig figs are in this one, technically? Infinity. Yeah, it looks like there's one sig fig, but it's not. It's exactly one. 1.00000000 inches equals 2.54 centimeters, where that is an exact number as well. So they actually have infinite sig figs. At first glance, you might want to put 1 sig fig for that 1 inch, but it's not. It's not, all right? These are infinite. And what you'll see is that it's typically the value you start with is how many sig figs will be in your answer, because we're always multiplying by definitions and conversions and stuff. So the first measurement, that has a finite number of sig figs we relate to our answer. All right, so let's do the other one here. This is how tall I am, 59.5 inches, except when I have my high heels on, my high boots. Okay, so in this one, okay, going from inches to centimeters, where am I going to put the 2.5 this time? The top, yes, because if I put 2.54 centimeters on top, I put 1 inch on the bottom, so 2.54 centimeters up top. How tall am I? 151 centimeters. 3 sig figs again, all right? 3 sig figs because the 59.5 inches is 3 sig figs as well, all right? And so these ones are kind of straightforward, just one fraction. They get harder. We'll do some examples, all right? Sometimes we need to use multiple fractions to get to the unit we need. We can't do it in one step. All right, so those 2 examples, we used definitions. 1 inch equals 2.54 centimeters to get to our answer. There's other ways we can get equalities. It's all about collecting equalities. Something equals something. That's how we get our fractions. And sometimes units themselves have an equality embedded in it. And this is a really important skill to have, okay? So if you have a unit that has a fraction in it, so like something per something, mile per hour, gram per milliliter, mole per liter, those are equalities as well that we can use as conversion factors. So how we can turn a derived unit into a conversion factor. So here's an example, speed in miles per hour, all right? So here's a derived unit. There's a fraction embedded in it. So what we want to do is take the number and the unit in the numerator and set it equal to the bottom unit with an inferred 1. So I'll give you an example. Okay, if you're traveling at 60 miles per hour, in 1 hour, how far do you go? 60 miles. So there is our equality. See how I took the top unit and number and set it equal to the bottom unit with an inferred 1, right? So this 1 hour that I set it equal to, how many sig figs do you think that has? Infinite, yes. While 60 has, in this question, I'm trying to tell you it has 2 sig figs because I underlined the 0. So this would have like 1 or 2 sig figs, but this 1 hour that we set it equal to with the inferred 1 in the denominator actually has infinite sig figs because it's the 60 miles was measured, the 1 hour is inferred. All right, so from this derived unit, I have an equality that I can, choose top or bottom, whatever, depending on, where, what unit I want to go to. So here, how long does it take to travel? 140 miles, traveling at 60 miles per hour. So you might just memorize, oh, you divide by 60. But let's not fill our brain with things to memorize. Use the equality. If we're in miles right now, I'm going to put the 60 on the bottom. Yeah, 60 is going to go on the bottom because miles cancels with miles. I put hours up top and we see miles cancels. I'm left with hours. It takes 2.3 hours to drive this far. 2 sig figs because 140 has 2 sig figs. And again, I underlined that 0 to indicate that 0 is measured. So it's 60 miles, 60 with 2 sig figs instead of 1 because it looks like 1. All right, I think that's the answer. I don't know. Okay, all right, so let's do another one. Okay, so practicing derived units, okay, and the trick there, the denominator gets an implied 1. So here's density. Okay, so the density of something is 1.29 grams per milliliter. So let's write a equality. What would the equality look like? We take the top number and unit and we set it equal to the bottom unit with an inferred 1. So this means if I have 1 milliliter of liquid, it weighs 1.29 grams. So this allows me to make a relationship between volume and mass via the density for a given substance, all right? So again, no different than miles per hour. I took the top unit and its number, set it equal to the bottom unit with an inferred 1. And this is useful to us because we can make the conversion here. I have 250 milliliters of fluid. How many sig figs does this have? 3, yes. Why does it have 3? I underlined the 0, yeah. If I didn't, then it would have 2 sig figs. Okay, so 250 milliliters. And I tell you the density, how much does it weigh in grams? So let's use the conversion factor, or the equality. Where am I going to put the 1.29, on the top or the bottom? The top this time, to cancel the unit, 1 milliliter is going to go on the bottom, and then 1.29 grams is going to go up top. So milliliters cancels, I'm left with grams. This thing weighs 323 grams, 3 sig figs, because all my numbers here have 3 sig figs. All right, so some of you might be sitting there thinking, well, I know density equals mass over volume, why can't I just use that? Do you want to memorize more equations? No, it's all just units. It's all units, okay? You don't have to memorize anything, right? I mean, if you want to, you can, but you can just unit your way out of it, okay? So there we go. And so that's a really important skill, collecting equalities, setting something equal to something so you can make the conversion factor the fraction that you want. I really urge you in like the starting weeks of dimensional analysis and all the types of questions you will encounter, take the time to write the equality. If I give you a density like 0.88 grams per milliliter, take the extra 2 seconds to write 0.88 grams equals 1 milliliter. So you can clearly see, oh, I have the skill, or like, you know, the trick to turn a gram into a milliliter if I want to, right? Take the extra time to do that now, and then you won't have to do it 3 months from now. Right? If you practice it now and really see it, how these units can convert from one another, you won't have to do it later. All right, so let's do some more practice. A question that you might be able to do in your head, but again, I want to show you units always win. We'll get you where you want. Okay, so how much does it cost to travel 105 miles? This is my daily commute when I come into work. My round trip commute. If your vehicle averages 34 miles per gallon and gas costs $3.91 per gallon. Let's ignore sig figs here, okay? So these 2 pieces of information I underlined, these are equalities that you can use. We can set something equals to something else, right? You might be able to calculate this in your head. I don't know. You might have done it when you drive. You're like, okay, my car gets this MPG, gas costs this much, this is how much it costs me to drive a mile. You ever think that? Maybe some of you have thought that, but the units will get us there. So let's take these 2 equalities, or these 2 pieces of information, and make our equalities. All right, so 34 miles per gallon. What does that mean? If I travel, or if I spend 1 gallon, how far will I go? 34 miles. So 34 miles equals 1 gallon. $3.91 per gallon. This means if I buy 1 gallon of gas, it costs me $3.91, right? So there are units that I can utilize in my fractions for this setup, because this one, it does require 2 different ones. We can't just do this in one step. All right, so I'm going to start with the piece of information given here that's not an equality, it's not a derived unit. I'm going to start with 105 miles. So which equality am I going to use here? Which is the only one I can use, the first one or the second one? The first one, where am I going to put 34? On the bottom, so 34.0 miles is 1 gallon. Now I'm in the unit of gallons. So I'm going to use this second equality, but the money goes where this time? Top. Yeah, so that puts 1 gallon on the top, bottom, and then $3.91 up top. And we see gallons now cancel, and I'm left with money as my unit. All right, and so that gives me about $12 as my round trip commute to school from the farm. All right, so there's an example where we did 2 conversion factors next to each other. It gets harder than this, all right? But don't be scared. You keep changing the unit, converting the unit until you get the thing you want. All right, so let's do another one. All right, I have a lot of large and small engines to take care of on the farm. Yesterday, I just bought myself a John Deere Gator. Yeah, it's like a golf cart thing with a dump bed. I don't know why. It was really cheap. We bought it used. We couldn't pass it up. We don't need it. We don't have room for it. Anyway, we have a lot of small and large engines to take care of, change the oil, blah, blah, blah. You can't just put used motor oil down the drain or into the environment. That's bad. Instead, we collect our motor oil and we actually bring it to the farmer down our street when they burn it for their heat in the winter. All right, so that's what they do. So we collect it all year long. And so if we store our used motor oil in this 48 by 40 by 46 inch tote, let's figure out how much it weighs if we completely fill it with motor oil. So I give you the dimensions of the tote, right? And so since this is like a square thing, we should be able to get the volume, right? If we multiply those numbers together. And I give you the density of motor oil, right? So we see density with that fraction there as a derived unit. So again, let's not be lazy. Let's take the time and write the equality that comes from density. What do we write? That's more useful to us. 0.88 grams equals 1 milliliter. The bottom unit with the inferred 1 equals the top unit and the number. All right, so this will be useful for us. Again, do not skip this step. Do it 100 times before you're allowed to skip it. All right. This allows us to go from a volume to a gram amount, right? Because the whole point of this is I want to figure out how much this weighs. I can figure out the volume of the tote, of the canister, but the problem is if I multiply all these numbers together, what's the unit that comes out of volume? Inches cubed. Is that compatible with milliliters? No, it's not. What's the one thing that I wanted you to memorize? 1 milliliter equals 1 centimeter cubed. So we need to memorize that. That's something you need to memorize, right? And technically, this piece of information and these two pieces of information are what you need to solve this problem. All right, where only this 1 milliliter equals 1 centimeter cubed, you do have to memorize that. But these two, no, you don't need this one. Actually, we need these two, this one and this one. These two we would have to give to you to answer this question. All right, so let's figure out the volume of this canister. So if I multiply all of those things together, all those values, we get that the volume of the canister is 88320 inches cubed. All right. I see that these numbers have 2 sig figs. 40 looks like it has 1, but it should have 2 sig figs as well, especially if we use the same ruler, okay, to measure the dimensions. So volume should have 2 sig figs, but I'm not going to pre-round. I'm going to keep that number. Just understand that it should have 2 sig figs. So there's my volume. It's not compatible with density. So here's my strategy. I'll write this in the corner. So we're starting with inches cubed. That's my volume. In order to get to milliliters, it's probably beneficial if I get it into centimeters cubed first, right? Inches cubed to centimeters cubed. Now I can get to milliliters using the 1-to-1. Then once I'm in milliliters, I can get to grams using density. And then from grams, what do we want? We want this in pounds. All right, so that's my strategy. This is going to take at least 1, 2, 3, 4 steps. Each arrow is some type of fraction that I need to multiply by. That's my strategy. So let's start with that volume amount, okay, inches cubed. So I'm right here. I want to get to centimeters, so let's use this second boxed conversion, inches to centimeters. I'm going to put inches on the bottom. Centimeters up top, but what's the problem? I need to cube the whole thing because if we're talking about inches cubed, there's 3 inches there, right? So if I just put 2.54 centimeters, I only converted 1 of them. So I have to take that whole thing and I have to cube it. I got to cube it. This step is equivalent. There's another way you could do this. Couldn't you just take each of these inch measurements, convert them to centimeters, and then multiply them together? That is the same as what I just did right here, right? It's the same thing. That I just multiplied each of these numbers by 2.54 3 times. Did I mess up? inches to grams. So an inch is what kind of measurement? You would use, it's a length, and a gram is a mass. Yeah, so that's not equivalent here because we don't have a relationship to relate those two things. But we do have a relationship to relate volume and mass. All right, so that's not out of the ordinary that we convert one unit to another, but we don't have that conversion. All right, so yeah, inches to centimeters cubed. All right, so this is what I would put in my calculator: 88320 times 2.54 cubed. So do know when I cube something, it's on the top and the bottom. But 1 cubed is 1, so that's fine. All right. Okay, so inches to centimeters. Okay, what's next? So I'm here now. Now centimeters to milliliters. So this one's straightforward. It's 1 to 1. 1 centimeter cubed is 1 milliliter. Cool. Now I'm in the unit of milliliters. So now I'm here. Now I want to go to grams using density. So where am I going to put the 0.88, top or bottom? Top. Did you memorize that? No, you just look at the units. If I put 0.88 on the top, that makes me put 1 milliliter on the bottom, so then that unit cancels. Perfect. Okay, now we're in a mass. Great, but I want this in pounds. All right, just because that makes more sense to me. And so I give you another definition. Again, these boxed definition, we'd have to give these to you. All right, these you don't have to memorize because it's imperial to metric. But do know the metric conversions. So grams, I'm going to put the 453.6 grams on the bottom, and then 1 pound up top. Okay, 1 pound up top. And so, yeah. So in my calculator, I would do that times 0.88 divided by 453.6 grams. All right, and so that gives us 2,800 pounds. That's how much this weighs. It won't fit in the bed of the truck, but it will fit on a class 2 hitch pulled on a trailer. All right, so yeah, this question had a, the cubic realm conversion. We use density, a derived unit. Okay, all right, did I do something wrong? Why didn't I? Oh, I did. I just didn't cross it out. They do cancel out, yeah. So this cancels with that, as this cancels with that. Yeah, both of them cancel. I just didn't cross them all out. Yep. Okay, and then the last one here, grams cancels out with grams. So you see the pattern. Boop, 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 boop. Great. All right, so this one, we converted a volume to a mass amount using density. So let's see if we can do another one. Okay, so dimensional analysis also works if you have to convert the unit in the top and the bottom, all right? If we have a derived unit like velocity, meters per second, and we want to convert it to another derived unit like miles per hour. Both of those are velocities, right? Dimensional analysis also works if you need to convert both the bottom and top unit. You just need to do them one at a time, all right? And the whole idea is you just cancel units, that's it. So this question will actually really help you. The last homework question is about a goose. Do you read that, about the goose, right? The kinetic energy of a goose. And so kinetic energy is 1/2 mv squared, right? But the trick with kinetic energy is that in order to use that equation, mass has to be in kilograms. Is the goose's mass in kilograms? No. And then velocity in 1/2 mv squared needs to be in what? Meters per second. Did the homework question give you the velocity of the goose in meters per second? Nope, they gave it to you in miles per hour. So really that goose question is a unit conversion question, not really a kinetic energy question. All right, you gotta massage the data before you put it into the equation vending machine. So this question is gonna help you with that. It's just backwards. We wanna convert the speed of light in meters per second to miles per hour. So for the goose, you'll just do it backwards, but it's still the same thing, just backwards. So let's do this. Okay, so the speed of light is that. What is the speed of light in miles per hour? So both of these are derived units. So I'm going to write this derived unit as a fraction. All right, so the velocity is 3 times 8 meters per second. So I can write this as 3.00 times 10 to the 8 meters over 1 second. So my strategy here is I want to turn the meter per second unit into miles per hour, where I need to convert meters to miles in a step, and then seconds to hours in the same line. I just have to do them one at a time. All right? For fun, use your best chemical intuition. If I give you the speed of light is 3.00 times 10 to the 8, how many sig figs do you think my answer will have in miles per hour? 3, yes. Because we start with 3, we're going to multiply by a bunch of definitions and conversions that have infinite sig figs. So our answer is probably also going to have 3. So don't like overthink it. Okay, so the whole thing, we have to convert meters to miles, seconds to hours, one at a time. Which one do you want to do first? It doesn't matter. Meters first, okay. So what piece of information do we need up here? Meters and feet, feet and miles. So these boxed green ones we'll use. Again, I have to give you these to answer because they're imperial stuff. So meters. 1 meter is 3.2808 feet. Good? Yes. But now I'm in feet per second. I want to get miles. So I'll go one more. All right. So that 5,000 number is going to go where? Bottom. Yep, because I'm in feet right now. So 5,280 feet is 1 mile. Great. If we finished this up right now, we would be in miles per second. I don't want that. So I converted meters to miles. Now I need to convert seconds to hours. So some more conversions that technically I didn't give you, but hopefully you know what this is. 1 hour is 60 minutes, I think. Yeah, okay. 1 minute is 60 seconds. Yeah, okay. Again, no memorizing, oh, to get from seconds to hours, I need to divide by 60, because technically we don't, right? Don't be memorizing things like that, because we just want to cancel units, because something interesting happens here. So again, we want to now convert seconds to hours, be cognizant of how we cancel units, because now seconds is on the bottom. So if I use this second equality right here, where am I going to put the 60 seconds? On the top this time, because 1 second is on the bottom. So 60 seconds is actually going to go on the top. 1 minute is going to go on the bottom. So now if I finished right now, what would my unit be? Miles per minute. Yeah, miles per minute. But so we're not quite done. Go one step forward, 1 step further. So 60 minutes goes on the top. 1 hour goes on the bottom. So don't fall for the trap of like, oh, to get from hours to seconds, I multiply by 60. No, it's all different because seconds is actually on the bottom.
Could you just kind of bypass the minutes by just multiplying 60 by 60, since 60 seconds and then 60 minutes?
Yeah, so the question is, can we use a different equality? Yes, there's another equality. 1 hour equals 3,600 seconds. Yeah, you can use that too. Because here, what is 60 times 60? 3,600, so it doesn't matter. I personally don't memorize this, all right? But I do know 60 minutes, 60 seconds thing. Yeah, it doesn't matter. Yeah. I don't know how many meters are in a mile. Do you? Yes, yeah, that's why. I don't want to memorize how many meters are in a mile. Yeah, if I gave you how many meters are in a mile, you could use it. But, yeah. No, the things that I boxed, those are things you don't need to memorize. That I have to give you those in order for you to answer this question. Yeah, so usually we expect you to memorize metric prefixes. See how all of these are like imperial, like English American units, all right? So any like weird American unit things we give you, all right? Yeah, so it's like if we were talking about like meters to centimeters, no, that's fair game. but not this. So the things I boxed, we would have to give you to answer this question. So let's do one more. Did I get the answer? Yeah, all right. So yeah, we go real fast. Okay, light goes real fast. Okay, so this one is an example of an exam problem that I give you all the information you need to answer this question, not a lick more. There are some prefixes that you need to memorize here. All right, so my car's tire pressure is 32 psi. You ever go to the thing and you fill up your tires, it's like 32 psi, all right? Psi means pounds per square inch. That's a derived unit, right? So this question is cool because we are doing both change the unit in the numerator and denominator, and we have some squared business. Yes. So what is the pressure when expressed in grams per meter squared? So the strategy here is the same. We are given the unit pounds per square inch, so pounds over inch squared. We want to go to grams per meter squared. And so the strategy is we need to convert pounds to grams and convert inches to meter, or inches squared to meter squared. But we just do so one at a time. Okay? So I'm going to rewrite this 32 psi as a fraction so it can help me determine, okay, I need to convert the top and the bottom unit. So I can rewrite this as 32 pounds per 1 square inch. Okay, what do you want to convert first, the top or the bottom? No, let's do the bottom first this time. Again, it's all multiplication, so it doesn't matter which way you do it first. So let's do the bottom first, where we convert inches squared to meters squared. I give you this equality. And so again, if this was an exam question, I would have to give you these two pieces of information at a minimum. So I'm converting inches, the bottom first. So I'm going to put an inch on the top. 1 inch is 2.54 centimeters, but what's the problem? You got to square it, yep. And so do know, again, if you square the whole fraction, you square both the top and the bottom. So in your calculator, you would write 32 divided by 2.54 squared. Right, the whole fraction is squared. So it's 1 inch squared on the bottom, 2.54 squared centimeters squared on the bottom, yeah. All right, so now I'm in the unit of what? Centimeters squared, but I want to go to meters squared. So this is a relationship you do have to memorize, centimeters to meters. But do you know how many centimeters squared are in a meter squared? No, you shouldn't, but do you have to know? No. You just need to know that there are 100 centimeters in 1 meter, and then do what? Square the whole thing, yes. So in my calculator, I'm doing 32 divided by that times 100 squared. So if I was done, my unit would be pounds per meter squared, but I'm not done. So I did the bottom. I changed inches squared to meters squared. So now I do, now I focus on the top. All right, and so I'm in pounds right now, and I want to get into grams. So let's look at this conversion that's given here, pounds to kilograms. Where am I going to put the 2.2? On the bottom, yeah, so 2.205 pounds on the bottom, 1 kilogram up top. All right, but I'm not done. I need it in grams. So there's one equation or one relationship I didn't give you here either, and that's kilograms to grams. All right, so what's the relationship there? 1 kilogram equals 10 to the 3 or 1,000 grams. Yeah, a gram is real small, kilograms real big. So the 1,000 is going where? Top or bottom? Top. 1,000 grams, 1 kilogram, and then you're done. All right, and so as a roadmap here, these 3 steps converted inches to meters, inches squared to meters squared. These 2 steps converted pounds to grams. There was 2 prefixes that you needed to memorize, but all the other things were given to you. So this would be like an exam style question. Does that clarify things? Yeah, yeah. I didn't catch that. So are you just saying put these two things together? The last two steps together? Okay, so you're saying you want to do 1 gram on the top, and then you want to put 1 times 10 to the 3 kilograms on the bottom. You tell me. If you put that into the calculator this as your last step, you will not get the same answer I have in the corner, all right? But here, I want you to think about this logically. How much is a gram, like in your head? It's like little, it's like a grain of rice. And then how much is a kilogram? It's like bigger, right? And so what are you trying to say here? You're trying to say 1 gram equals 1,000 kilograms. Does that make like, no, it doesn't. You're saying like a tiny grain of rice is equal to 1,000 dumbbells, all right? And so hopefully in your mind you think, oh, that's not equal to one another. Those aren't equal. So instead, so that just means like you have the factor right, but it's applied to the wrong thing. And this happens all the time to students. And so you need to recognize, okay, a gram is really small. I need a lot of them to make a kilogram. So it actually is 1,000 grams equals 1 kilogram. That makes more sense. Like a dumbbell is equal to 1,000 grains of rice or something. Does that make sense? Yeah. Okay. Yeah. You tell me. So the question is the 2 sig figs in the answer from 32 psi? So let's just go through all of the things. How many sig figs are right here? Infinite. How about right here? Infinite. Yeah, 2.205 might have 4 sig figs, but what wins? 2 or 4? 2 in terms of sig figs. This, infinite, infinite. So 2. Yep. What? The 2.2, I didn't say it's exact, all right? So, but regardless, if this was 4 sig figs or infinite sig figs, 2 sig figs here still wins, so it doesn't matter. Okay, good? All right, so that's it. So we're done with chapter 1. What does that mean? No, that's not what that means. No, it means chapter 1 homework is due on Monday at midnight. That's what it means. Okay, so let's move on to chapter 2. So I'll just remind you where to find those slides. Remember, we find everything on modules. Okay, so I have chapter 2 locked behind the syllabus gatekeeper quiz, but I think the majority of you have done it. So it's down here, and you see you can download the slides there. There are practice problems on every page. So let's just go back to chapter 1. There are the slides. Here are the practice problems, all right, that you can go through. Look at all those. Look at all those. Oh, look, that's a really cool one. What's this one? What are you doing? I need to renovate my bathroom. How many boxes of floor tile do I need to buy? Right? So dimensional analysis, very, very useful. All right. And also note here on the chapter 1 page are the videos from the subsequent lectures. So I usually post them in the evenings on the same day, usually when I get home, but I have really slow internet, so it takes a while. But they populate here, all right? And so you'll find chapter 2 will populate on this page sometime tonight, all right? So I think some of you have found the lecture videos, but that's where they live. You don't need to ask for them. There's no Zoom. I don't Zoom live because I can't focus on 2 things at once. So, okay, chapter 2. So grab those slides. Do make sure you have the right ones. I had to update these slides over the weekend, so make sure you have the right ones. Okay, so we're going to talk about the periodic table, atoms, molecules, and naming, all right? So note here in the corner, I say memorize names of polyatomics, their formulas, and charges now. This is around slides like 28 to like 31 or something, okay? So I expect when we get to that section, when I say NO3 minus, you know that means nitrate. Yes. Because I'm going to spend 0 time going over it, right? You're just gonna need to memorize those. We'll go straight into naming. So what we're gonna talk about in this chapter, atoms, and so some details about atoms of our periodic table, the building blocks of matter, and kind of some historical facts about how we got to our modern view of the atom. We'll talk about the periodic table and the elements, how to use the periodic table, and then we'll get into naming different materials based upon their structure. So we'll learn that there's different naming rules depending on what kind of substance you're looking at. If it's molecular or ionic, different naming rules. All right. So let's talk about the history of the atom. So that historically, so we have like our modern view of the atom. Hopefully if you've taken any amount of, I think you have to take some chemistry, right, to be in this class, like a little bit, okay? I feel like at a minimum you should know that atoms are comprised of subatomic particles, protons, neutrons, electrons. Do we know that? Okay, all right. I feel like that's not a stretch. The thing is that discovery of protons, neutrons, and electrons, that's actually a relatively new discovery. Right, like within the past century. For a long time, scientists thought atoms looked differently. Sciences actually kind of fell more under the idea of like philosophy for a long time. All right, where like, I imagine like Greek philosophers, they would sit under their olive trees and like talk about stuff. And so like, if you think about it philosophically, like you can have an apple, right? It's matter, right? Apple is matter. You could cut that apple in half. Is it still an apple? Yeah. You keep cutting it. Is it still an apple? Yeah. But then just do it like an infinite amount of times. All right. And like philosophically, what those Greek philosophers thought is like there has to be a certain point where it's no longer an apple. All right. And that's where the idea of the atom came from. All right. That you could take a block of gold and keep doing that. And at a certain point, it's no longer gold. All right. And so that's where the idea of atoms, nothing can be cut further than just the simplest building block, an atom. And so that's where Dalton's billiard ball model came to be, where that's the simplest building block, that atoms were just these like hard spheres that made up matter. And those were your Lego pieces, essentially. So that was true, or that was like the theory for 100 years. Until discoveries. There was some, modern discoveries, and one of those is the discovery of the electron. That rocked the chemistry world. Once we learned that electrons existed, we needed to change our model. And so the model went from Dalton's billiard ball to the plum pudding model, and then we discovered a really dense nucleus, and then that was the nuclear model. So we'll just focus on this first row, where it gets us closer to our most modern day model, but when we get to chapter 6, we'll talk about the actual true atomic model, and that uses the Bohr model, or the 100% correct model is the Schrodinger equation to model the hydrogen atom. So we'll talk about that in chapter 6, so you just gotta be patient. Okay, so let's talk about our philosophers and the idea that, okay, yeah, you can take a hunk of gold, cut it 1 billion times at a certain point, you can't cut it anymore. That's your atom. So Dalton had 4 different postulates with his billiard ball model, some of which are still true today, some of which aren't 100% true. So this first one with Dalton's billiard ball model says that each element is comprised of very small particles. That's true. Atoms, all right? And that, an atom of an oxygen element is different than the atom of nitrogen, and that's true as well. So the first postulate's true. The second one says all atoms of the same element are identical. So it says like, okay, all oxygen atoms, they look the exact same. All nitrogen atoms look the exact same. So at first glance, we might think that that's correct. It's actually a little bit wrong, but it's okay. We'll talk about isotopes. So yeah, a little bit different. You can have oxygen with different weights. We'll talk about that later. So that one ends up breaking down a little bit in our modern view. 3, you can't change one oxygen atom to another element like nitrogen. You can't do so with chemical means. And this is actually where chemistry came to be, all right? Chemistry started as alchemy. Alchemy is this, I guess, the science of trying to make gold. They wanted to turn other elements to gold, all right? Because like gold is cool and like worth a lot of money. So they took the time to try to turn lead, one element, into gold. So we can see through Dalton's third postulate here that that should be impossible to do, all right? because you can't turn one atom into another. And then the last one here is that atoms form to make compounds. So for the most part, most of these postulates are true, small little caveats, all right? And then this, this model was the model of choice for 100 years until we discovered electrons. That's what rocked our world, because electrons are not included at all in this model. It just treats atoms as these just dense balls, all right? Okay, so this is where I do my demo. Okay, so we're gonna pretend for a moment we don't know what electrons are, okay? And so we need to think like these scientists who'd never heard of an electron, don't understand like negative charge. All they're looking at are observations and trying to come up with conclusions on what these observations mean. So I have my demo here, all right? Okay, lights off. Lights off, okay. So write these down. Can you write these down? Yeah, because I'm gonna show my camera. We'll show the different observations of this cathode ray tube experiment. So this cathode ray tube experiment, we are going to be observing a stream of electrons, all right, being emitted from a cathode and anode, all right? We're electrifying like a piece of metal to make it emit electrons. But remember, don't, in your mind, like forget their electrons. Just think of them as this mystery beam that has certain properties, all right? So I gotta do my camera thing. So, all right, so here's my cathode ray tube. Okay, so I'm gonna electrify it. Okay, there we go. All right, so we see that? You see it? Yeah? Okay, so that green, eerie light, those aren't actually electrons, all right? The electrons are hitting a fluorescent screen so we can see them. We actually can't see electrons, so I have to like trick you. I have to like trick it to allow you to see it. All right, so this is just a fluorescent screen that allows you to see it. So what's the first observation? No, the very number one. Travels in a straight line. Is this traveling in a straight line? Yep, okay, great. All right, so now what's the second observation? Bent by a magnetic field. Yeah, so right now you're seeing the light being emitted from the electron, so let's see what happens. There we go. Woo, see it? It's bending. Ooh, that bends a lot. See it? All right, so if this magnet, if this is the if I flip it, oh yeah, so here, that's the negative side of the magnet. Here's the positive side of the magnet. What does that imply about this mystery beam? It's negatively charged, and that's what they were able to deduce, all right, from using the different sides of the magnet or the electric field. They saw what sides it was attracted to. They were able to discern that. All right, what's the next one? Turn a pinwheel, yes. Okay, so I gotta use the other one. All right, so gotta show the other one. All right, so this CRT had the fluorescent screen so you could see it. So this is also a CRT, but there's no fluorescent screen, so you won't be able to see the electrons, but instead, what we have in here is a pinwheel, all right? Can you see it? Can you see it? Yeah, okay, all right, great. All right, so you won't be able to see the beam. You see it? Yes. So mystery beam is doing this. So what does that tell us? If it can move, this mystery beam can move a pinwheel. What does that imply about that mystery beam? It has mass. It has mass and is able to turn that pinwheel. All right? So don't mistake this mystery beam for light, okay? Because light does not have mass. Okay, so don't mistake that like fluorescent screen as electrons. We're not looking at light, we're looking at a stream of electrons, which we actually can't see. Light does not have mass, and if you shone like a laser pointer at a pinwheel, it will not move, because light does not have mass. All right, so don't mistake that. All right, okay, there we go. What's the next one? It heats the tube. Yeah, if I let this go long enough, it'll heat the tube. So that implies that whatever mystery beam we're working with is highly, highly energetic. And then what's the last one? Oh, it'll It'll do it regardless. So right now, like the anode and cathode here are made of some metal. I don't know. I'm going to just say silver. It's made of silver. But regardless of what we made the anode and cathode out of, like if we did iron, gold, or whatever, this phenomenon will still happen. So it'll happen regardless of what we make the cathode ray tube out of. All right. So that's telling us that this mystery beam is an integral part of all elements. Right, so let's go back to my thingy. Okay, all right. So we are at number, 5. Okay, we see this phenomenon no matter what we make the cathode out of. And so the conclusion here is that this mystery beam is a highly energetic, negatively charged fundamental particle. So what are we looking at? What were we looking at all this time, or they were looking at? This is the electron, right? That all of this describes an electron. Travels in a straight line, positive charge, has mass, and is really energetic, and it's part of all matter. So we are talking about the electron, all right? So now that we know what an electron is, oh wait, no, that's the next slide. Okay. One other detail about J.J. Thomson's experiment, so he didn't just like discover or observe all those things. He was able to do other fine-tuned experiments, and he took this CRT tube, and he took a magnetic field and like bent the beam, and then he took a electric field in a different direction and unbent it and made it straight again. And so he compared the strength of the magnetic field and the opposing electric field, and he was able to calculate the charge to mass ratio of that mystery beam. So the important thing here is he learned that electrons existed, but he wasn't able to discern the charge of an electron, and he wasn't able to figure out how much an electron weighed, but he was able to get a ratio, all right? So his experiment wasn't like perfect here, all right? So he was able to calculate that charge to mass ratio for his mystery beam. So we need some more experiments here to help us really flesh out the full details of electrons. And that's where the next experiment comes into play. And that's Millikan's oil drop experiment. So his experiment determined the charge of a single electron, but it was there's some subtle details here. All right, subtle details. So here's the experiment. So unfortunately, I don't have a demo for this. So he took oil and he sprayed it. All right, he sprayed the oil, and like oil falls, right? Because it's gravity, right? Like everything just falls. All right, so he sprayed oil, but then he took like an X-ray machine and blasted those oil droplets with X-rays so they would pick up electrons. All right, so that's why I don't have that demo here. All right, so you'd pick up electrons. So those oil droplets became negatively charged. And then he took an electric field, okay? So the negatively charged droplets would be attracted to like the positive part of the electric field, right? So when he sprayed the oil, he irradiated them with X-rays to pick up electrons, then he applied an electric field to attract those negatively charged droplets to catch them. He caught individual droplets. He would do that whole thing. He would spray, irradiate, catch. He would just catch one droplet every single time. Every single experiment he did, he would catch one droplet and suspend it, that negatively charged droplet, between those charged plates. So he did this over and over and over and over again, and he calculated every time he caught a droplet, he was able to figure out how much that droplet, the charge of that droplet, right? Depending on the strength of the electric field that he was using, and using like gravity and the size of the droplet, he was able to calculate the charge that was attached to every single drop that he did. So he did this thousands and thousands of times, and he got data that looked like this. So each of these bars is a trial. It's a trial, and it shows the charge of one oil droplet in one experiment, all right? And so the brilliance of Millikan and why he got a Nobel Prize here is how he interpreted this data, all right? It just looks like a bar graph to you, right? And so the question is, well, what's the important information here? Is it the whole point here is we want to determine the charge of an electron. So is it the shortest bar? Is it the average of all the bars? Is it the tallest bar? You know, or is it the bar that shows up the most, the same number, the most times? You know, so that's the question of, you know, how to interpret data. It's actually none of those things. The charge of the electron, how we interpret this graph, is actually the increment between trials. The smallest increment between trials, because the difference between this trial and this trial is 1 electron. The difference between these trials and these trials is another 1 electron, all right? Because electrons, it's like a counting number. You can only have a integer number of electrons, right? And so that's the brilliance of Millikan, where it came out, is how he interpreted this data, that he determined, oh, electrons, it's like something you can gain. You can only gain 1 or 2 or 3 electrons, a counting number. And so he saw this increment of charge change between these trials. All right, and so that's the most important information. It's not the smallest, it's not the greatest, it's the increment between. Because technically, you know, you might think, well, you know, the smallest trial, does a droplet have to only gain 1 electron? It doesn't have to, all right? That trial could have been 2 electrons, 3, I don't know. But we see that the smallest increment was always this constant value, and that's where his brilliance comes out, all right? So it's the steps between the data. So let me show you in an analogy, because this topic is always hard for students. So pretend I sell lemons and I have a really poor business model. I don't know how much my lemons cost, and I don't know how many I sell. But you are tasked to figure out how much my lemons cost and how many I sell, just based upon the receipt totals from the cash register. So these are 6 customers that came in, bought lemons for me, but all you see are the totals. Can you, using your brilliant chemistry minds, determine how much my lemons cost? It's kind of just guess and check. Guess a number, check if it works. Can someone tell me how much one of my lemons may cost? Yeah. 25 cents. Who agrees with that? Yeah, 25 cents. 25 cents, yes, okay. Yeah, that works with this data, because the idea is, can you buy a fraction of a lemon? No, you can't. All right, you can only buy full lemons. So 25 cents works here. Would you have gotten into trouble if you assumed that this person bought 1 lemon? Would you have gotten in trouble? Yeah, because if you assumed that that person bought 1 lemon and 1 lemon cost 50 cents, some of the data doesn't work, right? Yeah, that this one wouldn't make sense, that one wouldn't make sense, okay? So how did we get 25 cents was the cost of a lemon? Smallest increment between, that makes sense with the data. All right, so yeah, what did we use? So it's not the smallest cost, okay, 50 cents is not the answer. It's not the largest cost, right? Because it is, you can buy more than 1 lemon, that's allowed. Like, I'm allowed to do that. It's not the average cost, it's the smallest increment between costs. All right? Can we deduce how many lemons each customer bought? Now? That we've like come to a conclusion how much a lemon costs? Yeah. All right, so this first person bought 4, this person bought 7, 6, 6, 2, 5. Yeah. Question? Yeah.
How do you know it's like 25, or how do you know that the smallest increment was 1 electron multiplied multiple electrons together?
Yeah, that's a great question. Do you have another price in mind?
Like
It could be 5 cents. You're right. Does 5 cents work? Could a lemon cost 5 cents? Yeah, it works. Because it technically, the increment doesn't have to be 1 lemon. Maybe my lemons come in bags of 5. We don't know that. And so that's why doing replicating experiments by other scientists was necessary. So the reason we know Millikan is right is because other scientists found out about what he was doing. They designed their own experiments and they got the same charge in different ways. So that's how we know. But you're right that technically we don't know if it's 25 cents or 5 cents, that both of them actually work within the data. Good job. Okay. But we're going with 25 cents. Okay, all right. Okay, there we go. Does that analogy make sense? Lemons are what? Electrons. Money is what? Charge, yes. Very good. Okay, so this actually came straight from an exam, right? But now you're good. So here's a bunch of data that Millikan got. So charges of oil droplets, all right? And now it's asking, what is the charge of an electron and how did Millikan determine this? So let's just look at the reasons. Technically, we don't even need to look at the numbers. So A, the trial that had the greatest charge. Is that how Millikan got it? Nope. Trial with the greatest agreement of the same charge? No. That just means that, he measured something with this many electrons multiple times. Trials with the smallest total charge? No, that's not, because does a oil droplet need to have one electron on it? Technically not. So if you were going to get this wrong, C is probably the answer you would have said, because most students assume it's the smallest one, or they assume it's the smallest amount, but you told me if we pick this one, we get into trouble, right? That it doesn't work for all of them if we can only buy an integer number of lemons. And so here's the correct answer, increment between data sets. And of course, it's not the average, right? And so we see that this about 5 times 10 to the negative 9 ESU is the increment between trials. All right, the amount between those trials is the charge of the electron that, like these, these guys could have, I think, maybe about like 5 electrons attached. These ones like 6 electrons attached. These ones 7 electrons attached, and so forth. All right, so you could figure that out if you divide this charge of a single electron by all of these different trials. You can see the integer number of electrons come out. All right, so that's the big idea with that experiment. Millikan didn't just discover the charge of an electron, but he interpreted that data in a very subtle way that was impressive enough to get a Nobel Prize. Okay, all right, so Millikan did the dirty work of getting the charge of an electron. J.J. Thomson got like kind of some crap data, a charge to mass ratio using the CRT, though he did discover the electron. He didn't get really good data. So with those two pieces of information together, now we can determine the mass of an electron. So we needed both of these experiments together to get that mass of an electron, right? So this is a test in dimensional analysis, all right? So I want the mass of the electron in grams. So look at this. It's a unit with a fraction in it. That's a derived unit. So we can build an equality from this. So remember how we do that? We take the top unit, so 1.7588 times 10 to the 8 coulombs is equal to what? Equal to 1 gram, yep. And so that's the fraction that we will use to get wherever we want. So let's take the other piece of information that's not an equality and start with that. So 1.6022 times 10 to the negative 19 coulombs. Okay, where am I going to put the 1 gram? Top or bottom? Top, yep, because if I put it on the top, then I get to put 1.7588 times 10 to the 8 coulombs on the bottom. 1 gram up top, coulombs cancel, and then we get this nice mass of an electron. It's real tiny, really small. Checking sig figs, this number has 5 sig figs. This one also has 5 sig figs because these are measured. These are measurements that they, measured in lab. And our answer also has 5 sig figs. All right, so good. Sig figs are all good. All right, so that's the experiments surrounding the electron. As chemists, we care most about the electron. We'll spend 2 slides on the proton and neutron, and that's it. We care most about electrons. They are involved in most of the chemical reactions that we will study in 1210 and 1220. So that's what we care about. They're the most energetic. Okay, so, yeah. Do you have to memorize that? So anytime you need to memorize something, I put memorize this in red letters. So no. Okay, so now that we know what an electron is, let's go back to Dalton's model. Did Dalton's model include electrons in his picture? No. So that means we need to come up with a new model that includes electrons. So J.J. Thomson comes up with the plum pudding model. So he's like English, and that's what they eat for desserts, I guess. But so as Americans, let's think about chocolate chip cookies, okay? So what J.J. Thomson did is he took the Dalton model, the billiard ball model. Now he knows negatively charged electrons exist, so he just dotted the billiard ball with electrons, like chocolate chips, all right? So now we just have negatively charged chocolate chips in our picture, all right? But atoms, they're neutral, right? Atoms are charge neutral. Electrons are negatively charged. So what must we also have present? Something that's positive. And that's where this detail comes from, all right? We got the negatively charged electrons, the chips, right? And so what you see is the positive charge spread throughout. This is like our dough, and that's positive. So that positive dough needs to be there in order for the whole thing to be charge neutral. And so that's a small detail, all right? That, you know, once we've discovered electrons, in order for everything to stay charge neutral as an atom should be, we need to have something positive that's present. So J.J. Thomson just kind of got lazy and just kind of spread it throughout the whole mass. But that's because he didn't have experiments to tell him otherwise yet. Right? So this plum pudding model is not correct either. I just wanted you to see how they got to this picture, right? That what made the most sense. They know electrons exist, they're negative, we gotta have something positive, so let's just spread it around. Okay, so we know that this is wrong. It took Rutherford to figure out where that positive charge actually goes to get us to our more recent model of the atom. So when we talk about Rutherford's discovery of the nucleus, he used radioactive substances to determine that. So let's just think about some types of nuclear radiation. So there's a couple here. There's more that you'll talk about in 1220, but this is fine for now. So there's 3 types of radiation: alpha, beta, and gamma. Note the language I use. Alpha, particle. It's positively charged. Beta, particle, they're negatively charged. If they're particles, they have mass. Versus a gamma ray, do rays have mass? No, they don't, all right? So they don't have mass. So there's a big difference there. And also gamma rays have no charge, okay? It's just pure energy. So let's think about this. Which of these radiation types do you think can turn a pinwheel? Can alpha? Yes, because there's mass. Whoops. Can beta? Yes. What about gamma? No. Okay. So only the pinwheel experiment can tell us that gamma rays do not have mass. Right? So, but the top picture here, what we can also do is send these types of particles, these radiations, through you guess it, a electric field. Okay? So if we send these particles through an electric field, only the charged ones will respond to it. Right? So here, an alpha particle, if you put it through an electric field, will deflect its way towards the negative side of the electric field. And that's what you see here. All right? Electric plate, those are your alpha particles. The blue line, those are your beta particles. See how they're deflecting upwards towards the positive plate? All right? So this experiment is telling us the charges. The pinwheel experiment would tell us what mass is involved. And then this yellow line, those are your gamma rays. All right, see how they just go straight through? And that's because gamma rays do not have charge associated with them. I don't know if this is a homework question. I forgot if I put it on, but I like that question. It showed this picture, and it was like a statement. It said like, true or false, using this picture means gamma rays have no mass because they go straight through the electric field. Is that true or false? So gamma rays go straight through, are undeflected by an electric field, so it means they have no mass. Is it true or false? Ooh, I hear both. Okay, talk to the person next to you for like 30 seconds and try to convince them if it's true or false. Okay, let's try again. So the statement is gamma rays are undeflected by an electric field, so therefore they have no mass. True or false? Oh man, it's false. It's false. Okay, let's break this down. Gamma rays are undeflected by an electric field. That's true. But why is it undeflected? It has no charge. It's true that gamma rays don't have mass. But that experiment does not prove it. What experiment will prove a gamma ray has? Yeah, it's the pinwheel experiment. Yep. So if I sent a neutral atom through that, a neutral gold atom, will it be deflected by the electric field? If it's neutral, no, it won't. Yep. And does an atom have mass? Yeah. So yeah, that experiment with the charged electric plates only talks about charge. Yes. I don't know if that's a homework question, so you're welcome if it is. Because I think it's just a true false, and it does really poorly. Yeah. Okay. All right. So what do these experiments have to do with the gold foil experiment? So the whole idea of this experiment is we discovered the nucleus, that there's this dense mass in the middle of our atoms, and now we're closer to like our more modern day of the atom. Because like right now, before going into this experiment, we thought atoms were cookies, all right? That they were just these, uniform kind of like doughy masses, all right? And so what Rutherford did is that he took gold. He used gold because it's really malleable and you can like pound it out so it's really thin. So it's really thin so you can have like a sheet of it and it's only like a couple atoms thick. And so what he did is he took alpha particles, all right? Alpha particles, remember, they're positively charged, they have mass, and he shot it at this gold foil, thinking because all of the atoms are uniform, he thought he would just see all of the alpha particles just blast through that gold foil, but he did not see that. He saw something a little bit different. He saw most of the particles, the alpha particles, went straight through. But he saw every so often a fraction of a percent of those particles got deflected, all right? Deflected somehow. So this tells us two things. Since 99.99% of the alpha particles went through the gold foil, it's telling us that atoms are mostly empty space, that the alpha particle is coming through and it's not hitting anything and it's going straight through, all right? So that's the first thing of the experiment, that an atom is mostly empty space, but 0.5% of the time, an alpha particle would bounce all the way back to the detector, right? So that's telling us there's something really, really dense in the middle of that atom, that it's being either deflected or just bouncing straight back. And that's our nucleus. We can also discern one more thing about the nucleus. Sometimes the alpha particle was deflected away. All right, so if an alpha particle is positively charged and it gets deflected away, that implies it's being repelled by something. So that tells us the charge of a nucleus. What does the charge of the nucleus have to be for that alpha particle to repel away? Positive, all right? So we were able to get a ton of information here. The nuclear model, positive charge, all the mass is at the center of the atom, all right? Okay, and so does the plum pudding model account for a dense nucleus? No, it doesn't. And so that's why the gold foil experiment is important here, all right? And so here, the last slides here, we'll talk about protons and neutrons. It's just 2 slides. So again, chemists care about electrons. Protons are positively charged. They're inside our nucleus. Same with neutrons, all right? So they used electric fields again to figure out protons because they're charged. All right, we got the charge to mass ratio of protons using CRT tubes also, but filled with a gas. And then the neutron was the last thing to be discovered. Why do you think? All these experiments have what in common? They use what? Charge, electric field. Neutrons have no charge. So they were a lot harder to find because there was no charge for them to move against. All right, and so it took nearly 2 decades for them to find that. Okay, so we still have 2 minutes, but I guess you guys are done. So then yeah.